The modern periodic table functions as a rigid mathematical graph, explicitly mapping the physical limits of subatomic forces. Memorizing directional trend arrows is a fragile MCAT strategy. Under the pressure of the exam, rote recall often collapses when faced with a complex exception. In 1869, Dmitry Mendeleev attempted to order the known elements by atomic weight, which first revealed periodically recurring chemical properties. This initial arrangement hinted at a deeper mathematical pattern dictating elemental behavior, even allowing for the prediction of elements that had not yet been discovered. Henry Moseley later revised the table, shifting the organizing principle from atomic weight to atomic number, the exact count of protons in the nucleus. This revision reveals that every periodic trend is a macroscopic manifestation of a microscopic electrostatic tug-of-war. Two opposing variables drive this interaction: effective nuclear charge pulling inward and the principal quantum number shielding outward. Understanding this internal electrostatic engine replaces memorization with predictive deduction, making MCAT answers mathematically inevitable. To build this model, we isolate a single horizontal row, a period, and observe the addition of subatomic particles from left to right. With each step to the right across a period, one proton is added to the nucleus and one electron is added to the valence shell. Because these new electrons are added to the same principal energy level, they do not effectively shield each other from the pull of the nucleus. This results in a higher effective nuclear charge, or ZEF, the net positive electrostatic charge that actually reaches and pulls on the valence electrons. Across the period, ZEF acts as an inward pulling force that grows significantly stronger with every additional proton. This increasing electrostatic pull from the positive nucleus physically tightens the outer boundary of the entire electron cloud. This horizontal increase in ZEF explains why nonmetals on the right side of the table hold their electrons more tightly than the active metals on the left. Shifting focus to a vertical group, we observe the sequence of elements from top to bottom. Moving down a group increases the principal quantum number, creating an entirely new filled inner electron shell. These intermediate inner shells physically separate the positive nucleus from the outermost valence electrons. This separation creates electrostatic shielding, a phenomenon that diffuses the inward pull of the nucleus before it can reach the valence shell. This vertical accumulation of inner shells overrides the increasing positivity of the nucleus, leaving the outermost electrons loosely held and highly reactive. The opposing forces of ZEF and shielding directly determine the physical size of the atom, the atomic radius. The strong horizontal ZEF pulls the cloud inward, meaning atomic radius decreases from left to right across a period. Conversely, vertical shielding expands the cloud outward, causing the atomic radius to increase from top to bottom. This makes atomic radius the exact physical inverse of all other major chemical trends. We apply this same logic to ionization energy, the endothermic heat input required to remove a gaseous electron from its atom. The high ZEF on the right binds electrons so tightly that ionization energy sharply increases from left to right. Because massive vertical shielding at the bottom of the table makes electrons easier to remove, ionization energy decreases from top to bottom. Physical size and ionization energy represent direct mathematical inverses, determined strictly by the underlying electrostatic push and pull. Electron affinity is the exothermic energy dissipated by a gaseous species when it gains an external electron. Halogens exhibit maximum electron affinity, aggressively pulling one final electron to complete a stable octet. Noble gases are the exception, with an affinity of 0, because their octets are complete. Electronegativity measures the attractive force an atom exerts on an electron, specifically within a chemical bond. Electronegativity values scale identically to ionization energy, steadily increasing up and to the right across the table. Fluorine's combination of high ZEF and minimal inner shell shielding makes it the most electronegative element. All four major periodic trends are different empirical measurements of the same electrostatic equation. Standard periodic trend lines do not predict the physical size of charged ions. Metals possess low electronegativity and easily lose their valence electrons to become positively charged cations. Losing electrons often strips away an entire outer shell, causing the ionic radius of cations to plummet compared to their neutral baseline. Nonmetals near the metalloid line have high electronegativity and must gain electrons to become negatively charged anions. Adding electrons to the same valence shell increases electrostatic repulsion, causing the ionic radius of anions to abruptly spike. Accurately predicting ionic size requires analyzing the specific mathematical gain or loss of electron shells rather than relying on neutral trends. Transition metals are unique for their ability to maintain multiple positive oxidation states. Their loosely held s and d orbital electrons allow these metals to associate with water or nonmetals to form complex structures. Forming these complexes splits the d orbitals into two distinct energy tiers. A specific wavelength of incoming white light is absorbed, supplying energy for an electron to jump the gap. The unabsorbed wavelengths reflect back, giving transition metals their vibrant colors. The same d orbital splitting and electron mobility that creates these colors also allows transition metals to easily lose or gain electrons across different oxidation states. This precise control over electron transfer makes them highly effective as cofactors in biological enzymes. We return to the blank periodic table grid. These derived trend arrows represent the necessary physical outputs of Zeph and shielding, mathematically locking every element into its place. These electrostatic properties explain the body's choice of elements. For instance, the minimal Zeph of sodium makes it ideal for rapid, soluble ion transfer. Understanding these boundaries lets you check any coordinate and deduce its chemical behavior without relying on memorization. True scientific mastery is achieved not by memorizing a map, but by understanding the electrostatic physics that built it.